Welcome to the Explainer. Today, we are diving deep right into the heart of your computer to tackle one of the most powerful and, honestly, one of the most dangerous concepts in all of programming: concurrency.
I mean, seriously, have you ever stopped to think about that? It feels like your computer is doing a million things at once. It feels like magic, but it's not. It's actually the result of a long, long battle against a fundamental speed limit that's baked into pretty much every computer ever made. Okay, let's get right into it. Our story really begins with a villain, a bottleneck, a single point of failure that every single instruction, every piece of data has to squeeze through.
And this villain has a name: the von Neumann bottleneck. Now think of it like this. It doesn't matter if your processor is a Ferrari. If it's getting its fuel, the data, through a tiny straw from the gas tank, the memory, it's never going to go very fast. It's always stuck waiting. Everything has to travel down that one single crowded lane.
So what do you do when the main road is totally jammed? The answer is kind of obvious, right? You build more roads. And that is exactly what computer scientists did. And this one idea, it changed absolutely everything. And this new path, this is concurrency. The core idea was a total game changer. Instead of trying to do just one thing at a time, but really, really fast, the question became, what if we could do lots of things at the same time? And that's the heart of it. That is sub-program level concurrency. It's the art of designing a program so that multiple logical tasks are all making progress seemingly at the same instant. This is the secret sauce behind multi-programming and time-sharing, and it's what makes our computers feel so incredibly powerful and responsive. But, and there's always a but, this amazing new power came with a huge danger. I want you to imagine a kitchen with a bunch of chefs all working at once. If they don't communicate and coordinate, you're not getting a gourmet meal. You're getting total chaos. Now, in our kitchen, let's think about the spice rack. It's a shared resource. You can't have two chefs grabbing for the salt at the exact same time. Only one can use it. In programming, we call that area of code that touches a shared resource a critical section. So, what happens when we don't enforce any rules? What happens when two of our chefs, our tasks, try to grab that salt shaker at the exact same moment? Well, the dish might end up with no salt at all, or even worse, twice as much. The result is just a mess. This mess has a name. It's called a race condition. And it's called that for a reason. It's literally a race between two tasks, and the final result of your data depends entirely on who gets there first. It leads to unpredictable, corrupted, just plain wrong data. Okay, let's walk through this because this is critical. Look, task A reads a value. It's 10. A millisecond later, before A can do anything else, task B reads the exact same value. It's also 10. Now, they both add 5. So A is holding 15 and B is holding 15. Task A writes its 15 back to memory. Great. But then task B comes along, totally unaware of what A just did, and writes its 15 back, right over the top. The final value should be 20, right? 10 plus 5 plus 5. But it's not. It's 15. A whole operation just vanished into thin air. In computing, that is an absolute disaster. So, clearly, this chaos wasn't going to work. Programmers needed a way to enforce some rules. They needed to forge tools that could bring some order back to our crazy concurrent kitchen. And one of the very first tools was invented by the legend himself, Dijkstra. It's called a semaphore. The analogy is perfect. It really is just like a traffic light for your code. Before a task enters a critical section, it checks the light. If the light is green, you can go. If it's red, you wait. It's a simple, elegant way to make sure only one task gets in at a time. Now, semaphores are powerful, but they're also a bit low level. It's easy to make a mistake. So that led to the next big thing: monitors. A monitor is a safer, higher-level approach. Think of it less like a traffic light and more like a strict kitchen manager. The manager holds onto the spice rack, the shared data, and also knows all the rules for using it. Everything is bundled together in one safe package, and the manager makes sure only one chef gets it at a time. Much harder to mess up. But then there's a third approach that's just brilliant. It avoids the problem of sharing altogether. It's called message passing. And the idea is, what if every chef had their own private set of ingredients? No shared spice rack. If they need to coordinate, they just send notes to each other. That's it. No shared resources, no race conditions, no problem. And you can see here, this really lays out the trade-offs. It's always about trade-offs, isn't it? Semaphores give you this raw, low-level control, but that makes them risky. It's easy to shoot yourself in the foot. Monitors are much safer, they're higher level, and message passing just changes the game entirely by getting rid of direct sharing. 3 different tools for 3 different ways of thinking about the problem.
Okay, so semaphores, monitors, this all might sound a little bit theoretical, a bit academic, but I promise you, these concepts are the absolute foundation for how modern programming languages, the ones you use every day, handle concurrency.
A perfect example is Java. You've all heard of Java threads, right? Well, those threads are our chefs in the kitchen. They give developers a real, practical way to create and manage these concurrent tasks. And how does Java stop them from creating chaos? It has built-in synchronization tools. And guess what they're based on? The concept of monitors we just talked about. That synchronized keyword in Java, that's basically a monitor right there in your code, keeping things safe. But look, the story doesn't end there. The quest for perfect concurrency, well, it's far from over. In fact, the battle is being fought on some new and really exciting frontiers. You've got entire programming paradigms, like functional programming, that try to solve the problem by just eliminating shared changeable data. If nothing can change, you can't have a race condition. Simple as that. Then you have something called statement-level concurrency, in languages like high-performance Fortran, where the compiler itself is smart enough to look at your code and automatically figure out how to run it in parallel. How cool is that? And all of this is more critical today than it has ever been. I mean, your phone has multiple cores. High-end servers that run the internet can have well over 100 cores. That one little road we started with has become a 100-lane superhighway. So, if there's one thing you take away from this, let it be this. Concurrency is not some advanced topic for specialists anymore. It is a fundamental, non-negotiable skill for every single modern programmer. If you want to build software that's fast, efficient, and reliable, you have to know how to manage all that traffic. And that leaves us with one final thought to chew on. We're moving into an era of massively parallel computing, with dozens of cores in every device we own. What new bottlenecks are we going to discover? And what brilliant new solutions, what new tools for order is the next generation of computer scientists, maybe even you, going to create?